Welcome everyone to our Design++ Fall seminar series. We host them typically every other Thursday. Some will have one Tuesday talk this fall, and every week it's at the same time and same link. This is this semester's lineup. So you can look at that as well on the website. For past talks, you can also take a look at the recordings. And so we'll host every week. We'll put the recording on the YouTube channel. So if you happen to miss it or you really liked it and you'd like to share it, feel free to do that. Also, just to introduce us from our side, Michael, Romana, and myself, we also take care of the day-to-day business of Design++ and the Immersive Design Lab, and we're happy to have any discussions in the future if you'd like to get in touch with us. But without further ado, and most importantly, I'm happy to introduce you today Nikola Marinčić. Nikola is a researcher investigating the relationship between architecture and information technology. And that's especially with the focus and challenges of AI and how that influences the field. So he has graduated as an architect in Serbia and later obtained his Master's of Advanced Studies at ETH, where he also studied the philosophy of technology and computer programming. So in 2017, he was awarded the ETH Medal of Distinction for an outstanding doctoral dissertation on the topic of computational models in architecture. During his postgraduate studies, Nikola worked 1 year as a guest researcher at the Future Cities Lab in Singapore, an interdisciplinary research program of the ETH Singapore Centre for Global Environmental Sustainability. So without further ado, I'm happy to welcome Nikola for the talk today. I'm going to stop share and you can go ahead. And you can go ahead and share your screen, Nikola.
So thank you very much. Thank you, Danielle, and thank you, Michael, for inviting me. So let me just quickly share my screen. Do you see my screen?
Yes. Yes.
Okay, then I will start. So the title of my talk is Unreasonably High Expectations of Mean-Centric Distributions. And if this sounds familiar, then you know where I'm coming from. This is a reference to one of the seminal papers in machine learning by Peter Norvig, who is a chief of research at Google. And the paper's title was The Unreasonable Effectiveness of Data, and it is a celebration of data-driven modeling in science and engineering. And right now everyone is using machine learning, and you all kind of know that when you have a good hammer, that everything looks like a nail. So although my research is about AI in architecture, I would also like to take a more critical perspective towards it, and I hope you will not mind. This talk will be about positioning the role of machine intelligence within architecture and other fields of knowledge that lie outside of science and engineering, within fields where the questions of efficiency, problem solving, and optimization are not the most important ones. The value of architecture for me lies somewhere else, and to address this value, I find the notion of the masterpiece to be crucial. And it can also help us to understand how architectural design relates to information technology. I will not try to define the notion of a masterpiece here. I will instead read an excerpt from one of the best texts I have ever read by Gertrude Stein, called What Are Masterpieces and Why Are There So Few of Them? So it starts. And so always it is true that a masterpiece has nothing to do with human nature or with identity. It has to do with the human mind and the entity that is with a thing in itself and not in relation. The moment it is in relation, it is common knowledge, and anybody can feel and know it and it is not a masterpiece. At the same time, everyone in a curious way sooner or later does feel the reality of a masterpiece. The thing in itself of which the human nature is only its clothing does hold the attention. I have meditated a great deal about that. Another curious thing about masterpieces is nobody, when it is created, there is in the thing that we call the human mind, something that makes it hold itself just the same. The manner of habits of Bible times or Greek or Chinese have nothing to do with ours today, but the masterpieces exist just the same, and they do not exist because of their identity. That is what anyone remembering then remembered them. They do not exist by human nature because everybody always knows everything there is to know about human nature. They exist because they came to be as something that is an end in itself, and in that respect it is opposed to the business of living, which is relation and necessity. Gertrude Stein, 1936, a very short excerpt of this text. Okay, let's go to the introduction. So what does data-driven modeling involve? Data-driven modeling is inherently greedy business. It is about taking as much as possible to feed a hungry machine learning model. And from the statistical perspective, for example, sampling, which involves us building a representative of some kind of population, then a larger sample means a better sample, and this strategy seems to be a reasonable strategy. And in many cases it is. But if our expectations of data-driven modeling are sufficiently high in domains like architecture, then there is some room for disappointment there. Big data needs to be encoded, and each data sample is encoded through various features that we attribute to it. The consequence of evolving populations is that the values of the features will vary among the different samples that we have. So they will form a distribution. And if we are interested in kind of consistently modeling the phenomena that we do, then we must think of the distribution of features as a probability distribution. And this simply means that we agree that the values that appear more often in the dataset are more probable, and those appearing less often are less probable. And if you are interested in generalizing or predicting something from our data, then the probability distribution of the sample should aim to resemble the population's distribution. So this is what we all know. So I would like to explore today a rarely talked about limit. The limit manifests itself in the interplay between the expectations that we have from our models, for example, the expectations of the application of AI in architecture, the size and dimensionality of the data, the nature of how things we care about are distributed versus how we assume or wish they are. Simpler machine learning models, they are usually limited in two aspects. First, we must engineer features for them to work well. And feature engineering is a problem of adequately filling in space for any future distinctions. So the late success of neural networks comes partially because of their ability to learn these features themselves. When we give them any hard enough but kind of explicitly defined task, for example, recognize what are dogs and classify dogs and cats, for example. The second limitation of these simpler models is fidelity. So they're prone to gravitating towards randomness as we increase the dimensionality of space. And this, in fact, is not a problem which is inherent to the models themselves. This is a problem which is intrinsic to high dimensionality itself. So the increase of dimensionality collapses the notion of metric distance, and I want to also demonstrate that today. And the advantage of simpler models is that given the well-defined features, which kind of is an art in itself to define those features, they allow us to predict or make distinctions which might need much fewer data. However, machine learning today has become really synonymous with deep neural networks, and given enough data and explicit directives, what they do is they learn to construct features that replicate those directives, kind of mimicking our judgment and also interpolating our mimicked judgment to unseen cases. And their most significant advantage is the pure fidelity of this mimicry. So they are not limited by the dimensionality of space because they do not rely at all to the notion of distance. So one can take all of these observables in the data and distill them into millions of dimensions, producing incredibly sophisticated mimicry compared to the simple models, kind of simple and relatively modest output. But then this comes with a price of requiring an enormous amount of data and computing. So the more dimensions you add, meaning the more sophisticated outcome you seek, the more data you need. And you need exponentially more data. So, but you can ask, is this still a problem if we kind of produce petabytes of data every day, no? On one hand, it is not a problem, but on the other hand, this is exactly where I believe that the problem of expectation lies. So what I would like to explore today is a thought that increasing sophistication in neural networks is hardly conditioned on exponentially increasing something else, which is by the nature of things generic and devoid of sophistication. In other words, neural networks are by design hard conditioned on the haystack, and we might be expecting to find needles there. Okay. To understand this point better, we need to talk a little bit about probability distributions, a little bit about high-dimensional spaces, the mechanics of machine learning, and mastership. So probability is about embracing variation. The theory of probability emerged from gambling halls and insurance brokerages and became a coherent branch of mathematics, with the foundational event being the publication of the book called The Art of Conjecturing by Jacob Bernoulli in 1713. So Bernoulli was interested in accurately estimating probabilities of events based on the number of their occurrences. And one of the significant achievements from Bernoulli was the idea of expectation. So how he introduced it in originally his book is kind of quite different than what we see in textbooks today. So he says, it can be seen from what we have said that we are not using the word expectation in its ordinary sense, according to which we are commonly said to expect or to hope for what is best of all, though worse things can happen to us. Here, account is taken of the extent to which our hope of getting the best is tempered and diminished by fear of getting something worse. So by its value, we always mean something intermediate between the best we hope for and the worst we fear. So Bernoulli conducted an experiment that involved 5,000 pebbles stashed in an urn, 3,000 white pebbles and 2,000 black ones. So the ratio of pebbles was unknown to the observer. This is why they were hidden from him. Yeah. So we can recreate an urn containing the required number of pebbles with the following code. So we take an urn and we put 3,000 of white pebbles and 2,000 black ones, and then we can render a sample from this 900, for example, because it's a nice round number, 30 by 30. So as you can see, there's a sample of this distribution. If we had, for example, 12,000 black ones, and we redid this, you would see that the black is dominating. However, we have 3,000 white ones and 3,000 black ones, so it's not completely clear which one is dominating here when we see it like this. Okay, so what Bernoulli did, he offered an interesting way to estimate the pebble color ratio. So the experiment involved repeating a simple procedure. So he draws a pebble, he writes whether it is white or black, and then he returns it to the urn. What he observed is, as the number of trials increased, then the ratio of white to black started to converge to a stable value. Okay, let's explore this. I'm gonna recreate his experiment in code. So the first thing that he drew was a black one, then the white one, then the black one, white one, black one, whatever, and then we go further, and these are his draws. Yeah. However, the another thing that we didn't do is we wrote it was black or white, but the another thing that we need to do is we need to count how many black ones divided by how many white ones we have at each one of these moments. So let's do that as well. So we start with the black one. So we're dividing by 0, so I have some kind of complex infinity. Obviously, you don't have to do that, but as you kind of start increasing these trials, you can see that this number is starting to move and approach something, and you can see something 9/16, 54/95. It's not really completely sure what it is. I will show you what it is. So the experiment discovered that as the number of trials increased, then this ratio between white and black pebbles converged to the actual proportion of 3/2. So the notion of expected value tells us what the result of an experiment would be if we repeated it a number of times. So as you can see, if I repeat it 1,000 times, instead of looking at those ratios, I can see that the value is starting around 3 and then slowly converging around 1.5, which is the ratio over 3/2. And this, so we can conclude that the expected value of the experiment is 3/2, but we discovered it by means of an experiment, so not theoretical. Okay. Soon it was discovered that not only the probability of an independent event converges to this expected value, but also the probability when you go away from the average also has some kind of distribution. And it was named the binomial of or normal distribution because its graph represented the shape of the bell. The name became the bell curve. So you can see it there from the video from Khan Academy. So whenever this variation of this large number of trials was observed in nature, the outcomes were kind of matching the binomial distribution in some cases. And indeed, some things in nature seems to be normally distributed, like height, birth weight, shoe size, multiple dice draws, similar matters. So the belief that emerged at that time is that somehow the average fate of these events is somehow maybe predetermined. And this was later formalized as the central limit theorem. So before we investigate the normal distribution and the issues arising from assuming it, let's us explore a much simpler distribution called an uniform distribution. So uniform simply means that all the outputs of a random variable are equally likely. So let us create a random variable r, which takes a value that is uniformly distributed between 0 and 1. So we created the r, so every time I call r, it's a different value between 0 and 1, and it's equally likely to be any value between them with no bias, yeah? I can show you this with a table, so I can create 100 of them, but this is not very useful unless we plot it. So let's examine the shape of the distribution for a different number of trials. Yeah. So if I make 10 trials and I plot the values that I got from 0 to 1, I get something that doesn't tell me much. Let's do 100 trials. So it's kind of slowly filling up this space between 0 and 1. If I add 1000, it's filling it more. We are not yet sure if it's really not biased, but let's do 10,000. It seems to kind of flatten out at the top. Let's do 100,000. It's definitely flattening, and let's do 1 million and hope my computer doesn't die. Yeah, it is definitely a uniform distribution, although we need to go towards infinity for it to become completely flat. So as the number of trials increases, the top of our histogram flattens out, which indicates that all values are equally likely. So now let's see how we can use the uniform distribution to construct a normal distribution. So let's do this. This is what we started from, a normal distribution. So what we need to do is we need to add 2 r's. Simple as that. When we add 2 r's, we get a completely different shape of our data, which you can imagine why is this happening. So the combination of r and r is randomly distributed between now 0 and 2, and you can imagine that some values will appear more often than the others. One on the poles will going to be much less probable. However, if we add r plus r plus r, we get something more and more similar to a normal distribution. If we add 4 r's, we get something that gets really quickly very close to a proper normal distribution. If we add a couple of more r's, it will be virtually indistinguishable. And then this is the behavior, this is the consequence described by the central limit theorem, which says central limit theorem establishes that in many situations when independent random variables are summed up, their normalized sum approaches a normal distribution. So their normalized sum, which is something I didn't do, let's normalize this sum by dividing this by 4. Now the values should be between 0 and 1, and this is what central limit theorem establishes. Obviously, this is just a model. Okay, so what are the parameters of the normal distribution? Well, normal distribution can be fully described by only using 2 parameters, which is mean, which kind of is the center of the distribution where it centers around, and standard deviation, or sigma, which defines how steep it goes, decays, yeah? But this doesn't mean that it actually decays less or more steep. That would be a false conclusion to make. It decays exponentially, yeah, on the ends. It's just that this is about scaling towards what the ranges of data that it covers, yeah. And these simple 2 parameters, that can be a good thing or a bad thing, as we will see later. So, how do these curves relate to probability? What characterizes all these probability distributions is that their area under the curve equals 1, meaning 100% probability. So the total probability of a probability distribution is always equal to 100%. In other words, the probability of getting any value between negative infinity and positive infinity is always 100%. Yeah. This also means that the probability of getting any kind of specific value, for example, 2, is 0%. Why 0? Because we are picking one value out of infinitely many. So to get a reasonable value for probability, you need to choose a range of values. For example, to calculate the likelihood of getting a number between 1.5 or 2, for example, between 1.5 or 2, or between 2 and 2.01. This also gives us some kind of probability. But 2 itself or 1.5 themselves, they simply, they have no probability. They are completely improbable because we have unlimited values to choose from. Okay, so the problem of computing the probability of specific value ranges is in a continuous distribution, which is like a normal distribution. As we said, it's equivalent to finding the area under the probability density function of that distribution. So let's do that. So you can see here that I can choose, for example, a range here, how to between like upper left bound, right bound. Here I have the left bound. Yeah, I can like calculate the probability that the value will be larger, for example, than 2, or larger than 4, and whatever. But let me center this a little bit because these two are connected. We put it back to 0. Let me put it back to 1, just to make it as standard as possible, just to see what I'm talking about here. So, and let's see where are we taking where are we computing the probability. So I'm computing it from 0.7 towards infinity. So we can use integral calculus to find the area under the curve. So integrate the curve in an interval, giving us the number of which corresponds to the area. And then this area will correspond to probability. So if we do this, we get a probability. So the probability of getting a value larger than 0.7 is 24.61%. So now look what happens. If I go find the probability larger than 2, it's only 2%. If I go larger than 4, it's only 0.004839%. If I go larger than 10, then there is so many zeros there that this is basically improbable. So that this will basically never happen. Yeah. Okay, so what are the problems when we assume a normal or a non-scalable distribution? So as I mentioned before, in the time of Bernoulli, whenever this variation was observed in nature, its outcomes seem to be following the binomial distribution pattern. And the tricky thing about probability is that it is concerned with things that lie on a very thin line between mathematics and pragmatics. And this line appears to get blurred when we are involved in a particular sterile form of pragmatics, for example, gambling. As I mentioned before, the effort to formalize this study did come from gambling halls. But although being very close to theory, gambling might not be a good object to study probability on. And if you look how most people learn what probability is about, is through kind of dice throws, coin tosses, and pulling a specific card out of a deck. Yeah, but casino, in principle, gives us a very misleading example of what probability is about. So it is a completely artificially controlled case where what happens in reality is really designed to be incredibly close with the theory. And also for a good reason, because closer you are to the theory, the more control of the outcome you have. Thus, your profit is more secure. On the other side, the chance events that we experience in our daily lives, they are way more severe than that you might expect. Their distributions have nothing to do with the Gaussian curve. And the even bigger problem today that we face today is that the models used in economic theory or finance, portfolio theories and whatever, they're all built under the assumption of a normal distribution. However, the distribution of wealth, for example, has nothing to do with the normal distributions. So just imagine if we are now in a talk and I do not know how many of us are joining this talk, but just imagine that if Jeff Bezos entered this talk, and if I asked you what would be our average wealth if he entered this talk, well, I'm assuming that we will all of us would be having more than 10 billion on our accounts if we took the average. As you can see, the finance has nothing to do with normal distributions. It's the upper limit is a number, and this number does not correspond to anything natural. So, as you might know, you heard of Nicholas Nassim Taleb. He's not a very popular author in academic circles, as he's very much dismissive of the academia. And sometimes I do not blame him too much. But still, we simply cannot allow ourselves to ignore his perspective on probability distributions. So the central one that he raises is that the crucial information about some phenomena, about the observables, would reside in the tails, while the center of the distribution, or this mean, is mostly generic, uninformative noise. And I think that this assumption also speaks volumes about what we consider to be a masterpiece, for example, but we will get to that later. So what is a fat tail distribution? So a fat tail distribution is one that opens up an opportunity for the unexpected to happen. It opens up space for those events that are different and unexpected. For example, a market crash or an architectural masterpiece. So mathematically speaking, fat tails that Taleb introduces formally, they mean that this decay away from the maximum value is not fixed and exponential, but scalable and asymptotic. So, so let me read actually what Taleb actually wrote about the fat tail distribution in his book, Statistical Consequences of Fat Tails from 2019. So he says, centrally, the thicker the tails of the distribution, the more the tail wags the dog, that is, the information resides in the tails and less so in the body, the central part of the distribution. Effectively, for very fat-tailed phenomena, all deviations become informationally sterile except for the large ones. So the center becomes just noise. Although the evidence-based science might quite not get it yet, under such conditions, there is no evidence in the body. This property also explains the slow functioning of the law of large numbers in certain domains, as tail deviations where the information resides are by definition rare. So the crucial information resides in the tails, where the mean is mostly just generic, uninformative noise. So that is very interesting. So what if we assumed that the variance is a random variable? This is the experiment that Taleb makes. So he shows that if we change this normal distribution formula, introducing a level of stochasticity in the notion of variance, or in other words, if we treat variance as the random variable itself, then we can observe an interesting phenomenon. So let's do this. So we have a normal distribution in green, and then we have a distorted normal distribution, which is distorted by me changing, like introducing stochasticity to variance, yeah? You can see that the curve changes a little bit. However, what you don't see is that even a slight variation of this variance introduces what are called the fat tails. And you are not able to see this on this screen, obviously, very well, but we will see the consequences of this when we compute the probabilities. So let's calculate the probability of the fat tails. So we have our normal distribution on the top, and we have our distorted thing here, yeah? So I'm now computing the probability from certain value for both of these things. So from the normal one and from the distorted one, from the one which has some stochasticity. So if I, here I see the value from which I'm computing the probability. So from value 0, for example, from value -4, the probability is 100%, but of distorted is 99.8%. However, if the probability from 0 is around 50% from the normal distribution because it's perfectly symmetric, and from the distorted is very similar, 44.86. But look what happens if I go further. The further I go, the normal distribution just completely cuts us off. So this will never happen. If we use this model to predict whether something will happen, it will not predict. So in the history of universe, it will never happen, this thing. Yeah. However, just slightly changing, introducing just a slight stochasticity, which we can assume it's happening also in real life, this thing becomes much more probable than this one. Yeah. So this is orders and orders of magnitude more probable, although it doesn't seem like that. Yeah. But even if we do it a little bit more extreme, then obviously this one is going to go berserk again. However, this is something that might happen. Yeah, this amount of zeros. obviously, just you need to keep in mind here, this is an experiment. Keep in mind that this is one of the mildest possible cases of fat tails, actually the mildest one that you can make. And I picked them just because they resemble the Gaussian, the normal. They are much more extreme distributions. Yeah. So for example, Pareto distribution. So it's a very famous distribution named after Vilfredo Pareto, who was a civil engineer, economist, and sociologist. And he initially used it to model phenomena such as distribution of wealth in Italy. So he noticed that around 80% of Italy's land is owned by 20% of the population. And then he applied this to other countries just to check if it matches, is the phenomenon is the same. And he actually concluded, yes, the same thing happens in other countries. Yeah. So Pareto looks like this. We plot it. And it looks a little bit different. You can see that it has much fatter tail. Here you can actually observe it. But let's calculate the probability just to show you that it works. So the probability from the value, from this value here, 1 is 100%. Yeah, that's the total probability. And let's choose the number, our number. So the probability that something is larger than 5 is 15%. Let's go higher. Probability that something is larger than 15 is, there's a great probability. There's almost 4.5%. Probability that something is greater than 50, still 1%. That's pretty reasonable, 1 in 100, yeah? Even the probability that something is as high as 100, which is way on the far right of this graph, it's still something doable, yeah? So this is more likely to be a phenomena that we are actually interested in this talk, yeah? So, unlike the normal distribution, as you can see, there's one more thing about Pareto. It is a scalable distribution, which means that if we were to compare significant outcomes, for example, comparing someone having $16 million with someone having $8 million, the ratio would remain the same as if we compared someone having 2 million and 1 million, or someone having 100,000 and 50,000. Yeah. So this means that it's scalable. But remember the shape of this Pareto distribution, because we will come back to it when we talk about architecture. Okay, let's talk about machine learning now. So the nice thing about it is that you do not actually have to know all the details of how machine learning works, as long as you make it, whatever you make with it, in, for example, architecture, not in engineering and science, obviously, as long as you make it kind of stand in its grind. You can even misuse it, yeah? And especially in architecture, this is maybe even more effective than if you actually know how machine learning works. For example, the more I understand how it works, the less convinced I am that it has anything to do with architecture. Well, for this presentation, it would be somewhat important that you know how neural networks work. And I assume that you already know, but if you do not, you can also find my course on YouTube where I teach neural network mathematics and how to implement them from scratch in Python. But how much data do these neural networks actually need? So a neural network, I would claim, requires an unreasonably high number of data samples to achieve a high quality output. For example, a binary classifier, which is the simplest of all applications of neural networks that we can make, requires around 60,000 images of human writing to precisely distinguish between 10 different digits. And then I experienced a much more extreme example when I was watching the Tesla's AI Day, where they described their self-driving models in detail. And as you know, their self-driving model, car driving model is not yet fully competent driver, yet their cars have recorded over 1.3 billion miles of driving in use. And imagine now each second of driving has 60 frames. So imagine now how much data that is. On top of that, they have 10,000 GPUs for training, and then they have a data labeling team which has 1,000 people, and they have developed their own machine learning powered labeling processes and all of that. Imagine now this machinery. However, even with all of this, the car still does not run as expected. Why is that? According to Tesla AI Days. Because as it turns out, the majority of driving does not convey too much information. Remember now Nikola Marinčić. And they have a lot of it, too much of it. So the distribution of all that data somehow centers around the mean. So what matters in self-driving and where car does it wrong is in the situations which happen very rarely. So the funniest thing I found was that there were actually people who watch videos of these cars that these cars record, and then they record unexpected events, and they record them in a list. And the problem is that this list grows larger and longer, and one cannot predict what the next thing in this list would be, because you cannot predict what crazy thing is going to happen on the road, which has never happened before, yeah? Because they cannot just fill this space of the unexpected, because we cannot know that. They have to simulate it with more or less random situations. So they created a realistic driving simulator in which they reproduce weird situations like the ones that you can see below. Yeah? And because the video takes just so long, I couldn't actually find it, but there was a video of like dinosaurs crossing the road, like people dressed in different costumes and dinosaurs crossing the road. And when you think about it, this makes a lot of sense, because it doesn't matter whether an actual dinosaur will ever cross the road. What matters is that the car stops when that happens, because something might one day resemble that dinosaur in this or that form, maybe not rational to us, but to a computer it might look like a dinosaur, and the car will stop and there will be no tragedy. So somehow this impossible thing starts to play a role, finally, in machine learning today. Yeah? So the fact is that Tesla trained its networks on 371 million simulated images and over 500 million labels of things that never happened. Yeah? And these things that never happened, these rare occurrences, are actually helping the car to drive better than before. These random situations that are completely absent from the original dataset. And this Tesla story is a great example for me to illustrate how the lack of evidence for something does not mean the evidence of absence of something. Just because they have no evidence that these weird things happen, they're not just automatically assuming that they're impossible. They're actually counting on them to improve their models, which is, I find, very interesting and great. And the self-driving car does not really work that well in these rare situations yet. However, it's improving. But these rare situations are actually the situations that are potentially deadly. So if we put ourselves in the position of a potential victim of an accident, then the rare event that the Tesla car hasn't ever experienced before is the most significant event. But we have learned in the modernity to think about traffic security a little bit differently. So we approach driving safety from the perspective of statistics. We say that if people die less in traffic on average, then the overall outcome is good. So only if you accept this assumption, which I do not want to force you nor to force you not to accept it, well, then the self-driving car is a good application of AI. So let's come back to our simple machine learning tasks. So even if you work with, for example, 60,000 things, the law of large numbers and the central limit theorem will still come into play. What would be the consequences? So the consequences is that a single misclassified data point has almost no influence on prediction. So a single mislabeled data point in the dataset influences predictions in an amount roughly proportional, that's my wild guess, to its occurrence in the dataset. So we could make a very rough guess that a single misclassified image in the MNIST dataset, which is these digits, would make the classifier's prediction 1 over 60,000 worse. Second thing is that machine learning models can be pretty mode-centric. As we have already seen, the most generic features lie in the center of the distribution, and the learning signal of the neural network is strongest in the modes. So what are the modes? I'll just run this. This is, of course, taking that these are not real modes of some distribution, but they often look like this. You must have seen it if you ever trained machine learning model, for example, GANs. So here we have a random multimodal distribution, and if you have worked with GANs before, then you know the idea of mode collapse, where a generator finds that the optimal method to fool the discriminator is to simply assume one mode, for example, one peak here, yeah, or in another one, this one or this one, yeah, and then makes only one really good image. For example, if the model is trained on dogs, then the model might only produce a picture of a Labrador because this is the dog that appears the most, or maybe it's the dog that has most distinguishing features. It's not really clear why this happens. Even by the person who discovered GANs wrote a paper, and then he contradicted himself later. So no one is really sure what is actually going on exactly in these things. Yeah. Okay. Finally, another thing that has a lot to do with the expectations from machine learning and has a significant impact on these data distributions that we just mentioned is the dimensionality of space. So let's talk about it next. So check out Michael Fabinger's work on that. He's a physicist and economist, currently a professor of economics in Tokyo. So thanks to Mathematica, I took his examples, everything I learned here and what I will show you, I learned from him, but I implemented it in Mathematica kind of quickly and interactively, which is why I chose it for this particular talk. So the idea is images are two-dimensional things when they are printed. However, digital images, the space of digital images is a high-dimensional space. For example, because this is a space of all possible images of the same size. Yeah. So, for example, if we digitally encode a color image, which is relatively small, for example, 1,000 pixels times 500 pixels, for today's standards, this is nothing. And if it's a color image, then this image has 1,500,000 dimensions. Yeah. All of these dimensions vary over different images. And in machine learning, we deal with probability distributions over high dimensional spaces. Over, for example, 1 million dimensional space, we are dealing with its distributions. Yeah. And since the observables belong to these high dimensional spaces, also what we learn also will reflect some of the space properties. Yeah. And this is something that we often overlook. So let me just break you here on intuition. The main idea here to understand is, as I will show you, that although formulas for calculating distances, for example, Euclidean distance or cosine or whatever, in spaces of any dimensionality, they all come from the same genus. The notion of distance itself changes qualitatively with increasing dimensions. So let me demonstrate this. Let me prove this to you. Here we have a formula for a ball, volume of a ball here, and we have two balls. I will create two balls here. One has a radius 1, one has a radius 9/10 or 0.9. Let's visualize them in 3D space. So the green one has the radius 1, the red one has the radius 9/10. And okay, let's do something here. Let's calculate the volume of the green ball, which is, we get the volume is 4 over 3 pi, which we know from maths. That's how you calculate the volume. And then volume of the inside ball would be 243 pi over 250. And if we compute the ratio between these, the larger over the inside over the inside to the outside, yeah, so red to green, we get that the ratio is 792 over 1000. Yeah. And this is the same number, funny enough, that we get if we simply take this lower number, 0.9, which is the radius, and do it to the third power. How do you say? Raise it to the third power. So you get the same number. So 72.9%, or this is the same as 0.729. So let's do it just to show you that it's the same. Let me do this in 2D. So this is a disk now. We have two disks. One is a red one is a green one, like analogous to this situation. The green one has a radius 1, the red one has a radius 0.9. And then we compute the area. The area is obviously pi. And the radius of the inside one would be 81 pi over 100. And if you compute the ratio would be 81 over 100. Yeah. And this is not surprisingly the same number which we get if we just raise 0.9 squared. The question is, what happens if we had a hypersphere within another hypersphere, which means we start from 2 dimensions with a disk, 3 dimensions with a sphere, and then what happens if we go to 4 dimension, 5th dimension, 6th dimension, 100 dimension? This is called a hypersphere within a hypersphere situation then, yeah? But we cannot visualize this, but we know what the formula would be. It would just be 0.9 to the power of the dimension that we are interested in, so n. So in 100 dimensional space, the ratio would be 0.9 to the 100th power, which is 0.02656%. So in 100 dimensional space, the inside of our object, which represents the 90% of its volume, takes up only 0.002% of the outside, which is something very unintuitive. But you could kind of see that this is happening because on the disk, it only took 81%. So the red is 81% of the green. And here it is already shrinking towards 72.9%. When we go to 100 dimensions, the inside to outside ratio is it's less than this. This is in percentages, 0.00 and then 0.0265556. Yeah. So the dimensionality compresses this ratio. So let me show you this. The volume ratio of 0.9 in two-dimensional space is 81%, then it drops to 72, 65, 59. In 20-dimensional space, it's only 12%, and in 100-dimensional space is 0.002. Yeah. Another example would be even more extreme if we had a sphere within a cube, and a disk in a square. So let's come, and then obviously if we did this to higher dimensions, then it would be hypercube in a hypersphere in a dimensional space. So, but let's compute it. So obviously hypercube is something that you cannot visualize, but in Mathematica there is a nice option called hypercube graph. So you do not see here. So this is one dimension, yeah, two-dimensional cube, three-dimensional cube. This kind of reminds us of the cube, but these are only the connections, yeah? So this is not actual space, this is just the connections, the graph, yeah? And you can see that if I increase the graph, only 9 dimensions, the cube is quite a different beast than our cube in 3-dimensional space. It's much more connected, it has 512 vertices, for example. It's a super connected thing. So let's compute the volumes. Hypersphere volume in 3 dimensions is pi over 6. So the sphere takes pi over 6 of the green, yeah. We can say n. I can apply n to this. This is around 50%, yeah, if you collapse the pi. But we can print the results, what would happen between these two objects. So the volume ratio of cube to sphere in 2-dimensional space is 78%. In 10-dimensional space is 0.02%. In only 20-dimensional space, this ratio is already 0.000002461. Imagine now an image which has 1.5 million dimensions. This ratio is basically approaching 0. And I'm interested to talk about what does this mean for us then. As you can see, this is if I plot it, you can see this collapse happening pretty quickly. As we increase the dimensions, this ratio is quickly dropping towards 0 and approaching it with asymptotic, very quickly here, yeah. However, we talked about normal distributions, so we should also examine that. So normal distribution in 1D space, this is what we seen, but as soon as we have millions or billions of images that we train our models on, this data is going to be distributed. So the features are going to be distributed, not in 1D like here. Yeah, where everything around 0 and whatever, although we can move that. It's going to be distributed in this high-dimensional space. So let's explore this. In 2D space, obviously, what happens is that we have something like this, yeah? And here the peak is around 0.4, and you can see that as soon as we start going to higher dimensions, the peak is going to be less, so 0.15. But this is because we obviously have to integrate this function from both x and y, yeah? So this is kind of where it comes from. The y peak lower. But what happens in n dimensions? So in Mathematica, I can kind of do it, but then I get certain variables that I need to unpack, and still these variables are not very useful for me because I still cannot visualize this thing in n-dimensional space. So what I can do is I have this formula here, which I learned from Michal. I can take a section through n-dimensional object, n-dimensional distribution, and what you can see is that this is 0.4 for 1D, this is 0.14. In 2D, this is 0.15, which is this 2D 0.15, you can see here. And then as you can see, this also collapses very quickly as we increase the dimension. So this thing becomes less and less pointed out, if you want to say so. Let's explore one more thing. This is the distance of a point from the origin. So you can imagine you have an origin of every space, how we describe it in Cartesian way. There is an origin 0, 0 coordinate, depending on the dimensions. If it's 2D space, if it's 1D space, it's only 1, 0, 2D space, 2 zeros, 3D space, 3 zeros, yeah, 3 coordinates. But we are interested in n-dimensional space. So this is the formula that I'm going to use. And something really, really remarkable happens here. It is, if we have 1D space, this is the normal distribution. look what happens with the distribution as I start increasing the dimensionality. So this is 1D space, this is the 2D space, this is 3D space, 4, 5, 6, 7, 8, 9, 10, 50-dimensional space. So we still have something resembling a normal distribution. However, this thing is concentrated, so the points which would be the mean of this distribution are going away from the origin, which means they're also kind of not only going away from the origin, but going closer towards the edge of the space, coming closer to the edge of the space. This is something very interesting to explore. So yeah, I'm going to leave this. So sampling in high dimensional, sampling from a normal distribution in a high dimensional space, I wanted to say, differs qualitatively from sampling in lower dimensions. The higher we go, the easier it would be for us to predict the value of this random variable. I hope you see where this is going to. So the same argument is from the other side. As we increase the number of dimensions, the probability of picking a point which is near to 0 is approaching, so this probability gets very low. It starts approaching 0. So the ratio of something closer to the mean to something which is further away from the mean compresses as well, in the same way as we saw this with these spheres. Yeah. So what is closer, what is further away, it compresses as well. So for the same amount of data, the more we increase dimensions, the space gets emptier, and what is non-standard becomes less and less important. So to compensate, we must increase the amount of data drastically to change the odds. Yeah. There are two aspects of this I'll explore here. So let's just pick an average distance between any 2 points, for example, in 3D. Yeah. So I have here a space. I have 60 points here because 60 allows me to still visualize the connections without exploding. So we have a space which is all of these points are within the region between 0 and 1. So you can see them here in 3D. And let's average distance. Let's show all the distances between all the points. Yeah, you see there are a lot of them. And now I don't care about the points anymore. I just care about the lengths of these lines. Yeah. So let's show the distribution of average distances in two-dimensional space versus high-dimensional space. This is in three-dimensional space. I want to have a distribution of these lengths, yeah, and sort them. So look what happens. We have in red two-dimensional space, and this is the distribution of the lines, yeah. This is obviously not 2D, but imagine that something similar is happening in 2D. So this is the distribution of the lengths. Yeah, some are longer, some are shorter. As you might imagine, some points, some are shorter, some are longer. Yeah? And this is the distribution. So look what happens when we increase the dimensionality of the space. So green is two-dimensional space. These two things start going away from each other. Yeah? So the lengths are in principle higher in n-dimensional spaces because simply space has more dimensions, and the values start going away from the average. But see also what happens when we make the ratio between the average distance in space and the size of the space. So this is now I'm talking about this thing. So not anymore of how far is it away from the beginning of the space. How far is it from the end of the space? All the values that we can have in this space. What you see happening when you increase the dimensionality is an even crazier increase of the mean. So you can see the mean values are starting to become much more important when compared to two-dimensional space. So in two-dimensional space, this now looks completely flat compared to 483-dimensional space, which only favors this mean, which only cares, most cares about this point here. Yeah. And the final experiment which I want to show here is the ratio between the shortest 10% of the lines and the longest 10% of the lines. So these are, again, this is the same scenario as here. What we want is we want to find what is the average 10% of the shortest lines versus the 10% longer lines. Yeah, and what is the ratio between shortest to longest. So I can do this with this code. With this code, I selected only 10% of the longest lines, and with the red, I selected only the 10% of the shortest lines. What I want to do with this, I want to compute now to kind of fold all the red ones into one average one and all the green ones into one average one, and then to make a ratio between the green and the average green and average pink. And this is what I get. So this is the ratio between the 10% of the shortest lines and 10% of the longest lines. So there is a distinction between shortest and longest, yeah, as you can see. Let's see what happens when we increase the dimensionality of space. So let's start with 1 dimension and go to 5 dimensions. So this ratio is quite high in 1-dimensional space, yeah? However, if we go to 2-dimensional space, this ratio goes to here. And the higher we go, the ratio becomes smaller and smaller. Already with 5 dimensions, this ratio is quite low, which means that these two things get more and more equal. Red starts approaching green, yeah? But let's see the final thing is what happens. This is now only first 5 dimensions. What happens when we go from 1 to 100? You can see there is a very quick collapse of distinctions between what is short and what is long. Yeah. So what does this crazy thing tell us about machine learning? So the more we increase the dimensionality, the more the average length of the shortest distances approaches the length of the longest distances. So the distinction between short and long becomes less and less sharp. And all the kind of older models which rely on the best matching unique and stuff like that, they start to fail because the nearest neighbor is not much closer than the other, than a random point in this space. So in turn, we are here forced to use neural networks because they do not have the notion, they do not imply the notion of space, notion of space. However, neural networks are data hungry, and we need to feed them with more and more data, which by the nature of things, how data is distributed in big data and in what we have in the internet, is just very much average and mode centric, and it's mostly uninformative average samples. Yeah. And another critical aspect of increasing dimensionality is that the space also gets increasingly emptier as we for the same amount of data. And yeah, I can show you just quickly what does this mean. So if you have space which is 5 by 5, if you want to partition the space into 25 things, in 3 dimensions we would have 125 cells. But if we increase the dimensionality of space, we would have a number of cells which is incredibly high, and it starts kind of being so high that it starts competing with the numbers of data that we have. And so the numbers of partitions, of distinctions, would start to compete with the number of data points. Finally, what does this tell us about architecture? I will come back to the text of Gertrude Stein and read it to you again. Some other parts. What are masterpieces and why, after all, are there so few of them? You may say, after all, there are a good many of them, but in any kind of proportion with everything that anybody who does anything is doing there, are really very few of them. Do you understand? Well, it really does not make much difference because, after all, masterpieces are what they are, and the reason why is that there are very few of them. I will now go back to this Pareto distribution here, and on the x-axis, I will make a little thought experiment. I will plot the masterfulness of an architectural project, and on the y-axis, I will put its probability density function. So what I would like to conclude with this talk is that masterpieces are rare, improbable, and carriers of what architecture is about. They are singular points referencing the whole of architecture. In statistics, data science, and machine learning, what is rare is called an outlier and is usually discarded as an error. In machine learning, a single data point means nothing, yet in architecture, that single point can mean everything. Thank you very much for your attention.